So today we begin the fourth session on Laplace transforms, and this will not be a very long session. We will finish this Laplace transform in about half an hour or 40 minutes. Then we shall start a new chapter. So let us recall, what did we do last time? We were discussing the convolution, right? We were looking at the convolution of two functions. What is the meaning of convolution? What is the definition of convolution, correct? And we looked at a few examples, right? And the examples we looked at was a characteristic function of the interval 0 to 1. And when you take the convolution of f with itself, of course, with the Heaviside function thrown in, we get a triangular graph, right? A continuous function. Yeah. So that's a typical of convolutions. When you take convolutions, it tends to smoothen, because you see, when you take the convolution of f and g, what are you doing? You are translating f of x minus t. So you are looking at the translates of f in some sense, and you are averaging it with respect to the weighting function g. So because an average, so the convolution of f and g can be thought of as an average of f with respect to g. And so whenever you average, you are going to get something better behaved. The ugly behavior will smoothen out to a certain stage. Alright. Now let us look at the convolution theorem. We are ready to state and prove the convolution theorem. If f and g are of exponential type, then fh convolved with gh is also of exponential type, where h is the Heaviside function. H is the Heaviside unit step function. So f and g are given to be of exponential type, then fh star gh is also of exponential type. Further, the Laplace transform of fh star gh is Laplace of f into Laplace of g. The Laplace transform converts the convolution into a product. The Laplace transform converts the convolution into a product. Excuse me. So what are we supposed to do? We are supposed to do two things. We are supposed to show that the convolution fh star gh is of exponential type. That is not clear. First we have to do that. So first we address that question. So let us first apply the definition of exponential type. F and g are given to be functions of exponential type, right? Which means that f is dominated by a1 e to the power omega 1 t, g is dominated by a2 e to the power omega 2 t, the first for t bigger than or equal to t1, the next for t bigger than or equal to t2. Obviously, I am going to take a to be larger than a1 and a2, omega to be larger than omega 1 and omega 2, t naught to be larger than t1 and t2, and I can surely arrange things such that, simultaneously mod f t less than or equal to a e to the power omega t, mod g t less than or equal to a e to the power omega t, both for t bigger than or equal to t naught, correct? This can be arranged. So another thing that you have to remember, that because f and g are of exponential type, the Laplace transform of mod f and mod g exist for s bigger than omega. The moment s is bigger than omega, then these two integrals exist, and we have seen this right at the beginning. The Laplace transform makes sense on the ray omega to infinity. So now we may take omega to be so large that this holds when s is greater than or equal to omega. Take a larger omega, okay, and so I can assume that s equal to omega is allowed, because I am going to work with mod f t e to the power minus omega t, mod g t e to the power minus omega t. The omega can be taken so large that these two things converge, right. Now let us proceed to show that the convolution of f and g is of exponential type. The proof is straightforward. It might appear to be a tricky, but this kind of a argument is used very frequently. So you are seeing it probably for the first time. So it might appear to you as a trick, but this is a very frequently appearing argument. You have to break up the integral into two pieces and you have to estimate it suitably, and the breaking is done in half into 2. So you take the you call h of x to be integral 0 to x f of x minus t g of t dt. It's called the convolution h of x. You break up the integral into 0 to x by 2 and the other integral from x by 2 to x. We have broken integrals before, but then the limits of integrals were constants, 0 to delta, delta to t naught, t naught to infinity in the proof of the Riemann-Lebesgue lemma. But here is slightly different way of breaking it up, but you will immediately see the advantage. You see, first of all I am going to assume that the x is large enough because I am going to get the exponential estimate for large values of x. For large values of x I am looking for the exponential domination. So assume at the outset that x is bigger than 3 t naught, right. So now you go from integral 0, look at this integral 0 to x by 2, f of x minus t gt dt. Now t is running from 0 to x by 2. So x minus t is running from x by 2 to x. T is running from 0 to x by 2. So x minus 2 will be running from x by 2 to t, and then x is bigger than 3 t naught. So x by 2 is bigger than 3 by 2 t naught, which is bigger than t naught, correct. So this function f of x minus t is less than a e to the power omega x minus t, simply because x minus t is bigger than t naught. So this whole thing has been dominated by replaced by the exponential function. Now look at this, a e to the power omega x can be pulled out of the integral, correct, and I am simply having e to the power minus omega t mod gt. And what did we say in the previous slide? Mod of the integral gt e to the power minus omega t is finite. So that the other thing is going to be a finite number. So you see that the first piece in modulus is less than a times a finite number times e to the power omega x. Same thing is going to be done with the other piece also. Look at the other piece. In the other piece, t is running from x by 2 to x. So gt is going to be less than a e to the power omega t. So that is a simple idea of breaking up the integral from 0 to x into 0 to x by 2 and an integral from x by 2 to x. Is it clear that that we have to break up the integral in this way? This is here the first part, x minus t is bigger than t naught, here t is bigger than t naught. So here we will apply use the fact that f is of exponential type, here we will use the fact that g is of exponential type. And the end result is similar in both the cases. We get constant times e to the power omega x. Each piece is dominated by constant times e to the power omega x. That is the argument, and that pretty much is all that is left. Alright, so I have formally put it here, mod of integral 0 to x by 2 f of x minus t gt dt less than or equal to a e to the power omega x. Remember I pulled out the a e to the power omega x outside, 0 to infinity mod gt dt e to the power minus omega t. For the other integral, this what I said, mod of f of x minus t, gt is less than a e to the power omega t. In this integral simply put x minus t equal to u, so that you get, instead of x by 2 to x you have 0 to x by 2, correct, and you have e to the power omega x minus u. Once again pull the a e to the power x omega outside, and then instead of 0 to x by 2 let it go from 0 to infinity, the less than or equal to sign, you have mod f of u e to the power minus u omega, that is also finite, correct. Take the larger one, let m be whichever is larger, two finite numbers, take the larger one and put that m here and the m here. So you will get that each of the two pieces is less than m a e to the power omega x. So total thing is less than or equal to 2 ma e to the power omega x, that is all, finished. So, okay, so the conclusion is written down, mod hx, which is the convolution of fh and gh, will be less than or equal to 2 ma e to the power omega x for x bigger than 3 t naught. Is it clear? Why the convolution is of exponential type? It is important to do this, you have to check, otherwise I can't take the Laplace transform, right. Of course, another thing that we have to show that something is of exponential type, that mod of the function should be integrable over every finite interval, as it should exist as a proper or an improper integral, that also has to be checked, but that is pretty easy, the same kind of thing will give you. You integrate the function h of x dx and you use the invert the order of integrations and you will get the answer. The second part is pretty simple, alright. So now we have established that the convolution fh star gh is of exponential type. Now what remains? We have to prove that Laplace of fh star gh equals Laplace of f into Laplace of g. That is the identity in convolution theorem. The convolution theorem has two pieces. The first piece asserts that the convolution fh star gh is again a Laplace transformable function, and then when you apply the Laplace transform converts the convolution into a product. This is very typical. This is the same result is true even for Fourier transforms. Fourier transform will also convert the convolution into a product. In transform analysis, it is a very common thing that happens, correct. Is that clear? Now suppose I take a sequence A0, A1, A2, A3, etc. To this sequence, I associate a power series A0 plus A1z plus A2z squared plus A3z cube, called the generating function, right. So sequence and a generating function, the sequence and its generating function, that is a kind of a transform, correct. If I take the convolution of two sequences, what will be the convolution of two sequences? A0 B0, A0 B1 plus A1 B0, A0 B2 plus A1 B1 plus A2 B0, generally summation Aj B n minus j. In the convolution, remember we had integral f of x minus t gt dt. Here it is a sum a n minus j bj. You see the analogy? Okay, so take this convolution of two sequences. What happens to generating function? It is the Cauchy product of the two power series. So once again, this so called Z transform, which takes a sequence and gives you the generating function, takes the convolution to a product. Same thing is happening again. So you see, it's a very characteristic business that happens in, it happens very frequently in transform analysis. That the Fourier transform is very nice. The other way around also we have. The product will go over to convolution. That's a very beautiful thing with Fourier transforms. In Laplace transform, a similar result is holds, but it's much more difficult to state. The product will go to convolution, but then the integral will not be over the real line. That's the problem. Just as the inverse of a Laplace transform is not an integral over the real line, it is an integral over a vertical line. So anyway, that we will come to when we do the Fourier transforms, if ever we do the Fourier transforms. Alright. Now let us come to the proof of the formula. Laplace of fh star gh. What is it? By definition, integral 0 to infinity e to the power minus sx times the convolution. What is the convolution again? It is an integral, remember, from minus infinity to plus infinity. I repeat, that is the definition of convolution, and I am using that definition. F of x minus t, h of x minus t, gt, ht, dt. Now, ht is 0 when t is less than 0. So, the inner integral goes from 0 to infinity, f of x minus t, h of x minus t, gt, dt, because h of t is 1 on the positive real line, 0 on the negative real axis. So, now I have two integrals, both of them going from 0 to infinity. I switch the order of integrations. The iterated integral, I switch the order of the iterated integral. The outer integral is with respect to x and the inner integral is with respect to t. I do it the other way around. I first integrate with respect to x and then choose to integrate with respect to t. So, outer integral is 0 to infinity gt dt, and the inner integral goes from 0 to infinity, because both integrals are from 0 to infinity. No? So, inner integral goes from 0 to infinity e to the power minus sx f of x minus t h of x minus t dx. Here you put x minus t equal to u, just a shifting of the variables, right. So, it is integral 0 to infinity gt dt, integral minus t to infinity e to the power minus s, x is t plus u. So, e to the power minus s into t plus u, f of u, h of u du. Now, where is t running from? T is running from 0 to infinity. So, t is non-negative, and here I am putting from minus t to infinity. So, there will be a piece from minus t to 0 and there will be a piece from 0 to infinity. What happens between minus t and 0? Look at this h of u here, that is going to be 0. So, really I do not have to worry about what happens between minus t and 0. So, all that remains is between 0 to infinity e to the power minus st, e to the power minus su, f of u du, pull the e to the power minus st outside, what do you get? Laplace of f, Laplace of g, correct? Is that clear? What is going on? It is a simple case of inverting two integrals, and what is written in red here, warning signal, we have to examine the validity of the exchange of two integrals, right. Exchanging the order of integration, that is something that needs to be justified. That is all that now remains, right. So, when can I switch? Okay, the way it is traditionally stated is that if for a non-negative function f of x t, integral a to b f of x t dx, integral c to d dt. You first integrate with respect to one of the variables, say x, then you integrate with respect to the other variable t. If this converges, if this is a finite integral, remember f is non-negative, that is a hypothesis, then the other integral will also exist, the double integral will also exist, and all three will be equal. This is the theorem. The theorem says that for a non-negative function, look at the three things, the double integral, the two iterated integrals. If one of them is finite, then all three are finite and all three are equal. But what is the condition for non-negative? Now, we do not have non-negative things here, but we have absolute convergence. When you put the modulus, it all works, that is enough. Then we reduce to the non-negative case. Na? Once you take the absolute value, then all three will exist with the absolute value, and so they will all three will exist without the absolute value also, correct. Is it clear? Is the theorem on when can you switch the order of integrals, and that condition is surely valid here. So, that is what the next slide, and here is the conclusion that the two integrals that we got were simply the Laplace of g and Laplace of h, and here I written down the condition that I just spelt out for you. I just told you exactly what the condition is, and I just written down the condition for you for your records, okay. What is written here is just what I said, that of the three things, the double integral and the two iterated integrals. If one of them converges absolutely, then all three will converge absolutely and all three will be equal, right. So, that completes the proof of the convolution theorem, correct. Is this theorem clear? Convolution theorem, one of the most important theorems in the chapter on Laplace transforms. It is absolutely important. Please make sure that you understand the statement and the proof very clearly. And the proof was very simple. It is just a question of switching the order of two integrals. Now, go back to the definitions that is given in the standard books. The convolution is defined as an integral from 0 to x, correct, f of x minus t g of t dt. If you use this, then you will not be integrating over a rectangle, you will be integrating over a triangular region. You have to be more careful when you switch the order of integration. Whereas by use of the Heaviside function, instead of integrating over a triangle, I am integrating over a rectangle, simply because the thing is 0 in the other piece. X minus t is positive, x minus t is negative, right. When you look at the diagonal x equal to t, take the xt plane, look at the diagonal x equal to t. One half of it is going to be x minus t positive, the other half is going to be x minus t negative. But the Heaviside function is 1 over here and 0 over there. So, instead of integrating over a triangle, I can integrate it over a rectangle by putting in the Heaviside function. Now, switching the order of integration becomes very easy. So, this proof is the same as the proof that is given in textbooks, except that you should recognize that it is the same, all right. Yes, it's I mean, it's not so explicit, but if you unravel what's going on, it is the same, all right. Yes, please settle down fast, because we have just finished one of the most important chapters, one of the most important theorems in this chapter on Laplace transforms, and you have just come at a time when we are finished. All right. Later. Now let us compute the convolution of t to the power a minus 1 ht and t to the power b minus 1 ht. Let us calculate this convolution. Remember, what is the formula? We did this and we got an ht outside. Please pay attention. We got the ht outside and we got an integral from 0 to t, yeah, t minus u to the power a minus 1 u to the power b minus 1 du, right. F of x minus t g of t dt, but instead of x I am using t, instead of t I am using u. The convolution is integral 0 to t minus u a minus 1 u to the power b minus 1 du, correct. So, now here you put u equal to tv, then you get the integral goes to an integral from 0 to 1, integral becomes integral from 0 to 1, t to the power a minus 1 minus v to the power a minus 1 from here, and from here t to the power b minus 1 v to the power b minus 1, and from the du piece you get t dv. So, all the t's can be combined, t to the power a plus b minus 1, h of t remains 0 to 1, our old friend 1 minus v to the power a minus 1 v to the power b minus 1 dv, the beta function has appeared. So, we have the formula t to the power a minus 1 ht convolved with t to the power b minus 1 ht equal to beta ab into t to the power a plus b minus 1 ht. What is the next step? Please tell me. No. What is the next step? Apply the convolution theorem. Why have we done all these things? Apply the convolution theorem to the whole thing. What are you going to get? What is the Laplace, what is going to happen? The left hand side will become Laplace transform of this into Laplace transform of this. Right hand side will be beta of AB into Laplace transform of this. Beta AB is a constant as far as t is concerned. So what is the, so recall what is the Laplace transform of t to the power k h of t? Laplace transform of t to the power k h of t is the same as the Laplace transform of t to the power k. Gamma k plus 1 upon s to the power k plus 1. Correct? So what is the Laplace transform of t to the power a minus 1 ht? Gamma of a upon s to the power a. The Laplace transform of this is gamma of b upon s to the power b, and the Laplace transform of this is gamma a plus b upon s to the power a plus b. So when I apply Laplace transform to this identity, what do I get? Gamma a into gamma b divided by s to the power a plus b equal to beta ab into gamma a plus b divided by s to the power a plus b. Cancel out the s to the power a plus b. What comes out is the beta gamma relation for which we have been waiting for so long, eagerly. Correct? Not sure whether you are so eager, but it is one of the most important things. And so let us look at this. So corollary is beta of AB, gamma of A plus B equal to gamma A, gamma B. So the proof is exactly what is spelled out. Let us go over it once again. We have t to the power a minus 1 ht convolved with t to the power b minus 1 ht equal to beta ab into t to the power a plus b minus 1 ht. That we have just proved. Take the Laplace of both sides. The Laplace of the left hand side is the product of the Laplace transform. That is the convolution theorem. Right hand side is beta of ab times the Laplace of this. The Laplace transform of t to the power a minus 1 ht is gamma a upon s to the power a. The Laplace transform of t to the power b minus 1 ht is gamma b upon s to the power b. So and Laplace transform of t to the power a plus b minus 1 ht is gamma a plus b upon s to the power a plus b. So out comes the beta gamma identity. All right. Okay. So now we have finished the proof of the convolution theorem, and I should give you a list of exercises, and I'm going to next thing that's the next thing in the agenda, but it's going to be difficult for you to write down all the exercises. So I'll just indicate which ones are sort of important. Just write down those things. I'll be putting it up on the Moodle anyway, so we will you will have it with you. So just write down the first, second, third, and the fourth. No, first, second. Just write down the first, second. Third is very easy, that the convolution is commutative. Fourth one, I'm even given the solution actually. So no need to write down the fourth one. The solution to the fourth one, you don't have to write down. First and second you write. The third one you don't have to write. You can just remember. The convolution, the order in which you take the convolution is not important. Just write the first and second. First and second are more computational, and I think we should do that in the tutorial class. Third and fourth, we'll come back to it anyway in the tutorial class, and we'll do it. So just quickly write it down. Just write the first and second, that's the most important.
If we take the convolution on two power series.
All right, yeah, let's go ahead. It's just the first two problems is all that I wanted you to write down. And here is another list which is very big, but I don't want you to write all the problems. I'll just want you to jot down just the first one. E to the power a equal to e to the power little e to the power at ht. Compute e to the power a convolved with e to the power b. More generally, compute e to the power e sub a1 star, e sub a2 star, etc. e sub ak. When a1, a2, ak are all distinct. Okay, just write these two. Sixth and seventh, you will have it in your Moodle, and at that stage of the game, you can read it at your leisure and do it. We don't have time to do all these things because from yesterday's list also we have lots of problems remaining for today's tutorials. Correct, and there are some more getting added today. So sixth and seventh, we shall just sixth is easy actually. Sixth is pretty simple, and you should think about it yourself. This is the definition. That's all. Nothing else. Seventh is easy for the case, but then you can do it at your own leisure. It's not. All right, just write down the fifth one. That's all. At the moment, that's enough. You just do the fifth one. That's enough for the by yourself. And here is a very important example on convolutions. I am putting this. So we saw that the convolution of x to the power a minus 1 ht and x to the power b minus 1 ht, right, was beta ab into x to the power a plus b minus 1 h. The convolution of t to the power a minus 1, t to the power b minus 1 we saw. Here is a generalization of that for n factors. For n factors, you will get, instead of the beta gamma relation, you will get gamma of a1 plus a2 plus an upon gamma a1 gamma a2 gamma a. You have to repeatedly use the result, and then just as the previous exercise had a integration part, a corollary of this also will have the corollary. Write down the ninth one. Write down the ninth one. Eighth one is a very famous problem due to Dirichlet, but that's easy. Although there is a Dirichlet's name attached to it, it's not pretty difficult. It's quite doable. And eighth one you can do it later. You can postpone it for a later time. But ninth one I think we should discuss, or maybe you should do it yourself. All right. Just write the ninth one. It's too long a list for you to write everything, each and everything. All right, so let us proceed with. Shall we go further? Okay. All right. Now, how does convolution theorems help us to solve initial value problems for ODEs? So take the simple example y double prime plus y equal to f of t. This we did not discuss yesterday in the tutorial. I said we will do it after the convolution theorem. So here it is. Y of 0 is C1 and y dot of 0 is C2. Okay, so take the Laplace transform of the differential equation. What do you get? S squared plus 1 capital Y as usual minus C1s minus C2. Where does the C1s and C2 come from? When you take the Laplace of y double prime, it is s squared times Laplace of y minus sy naught minus y prime of 0. That is where this comes from, correct. So now you wrote down this y as before as a sum of rational functions, correct, except that here you don't know the capital Fs. Here you don't know this function Fs. All right. So capital Y is the Laplace of little y. What is the first piece? It is the Laplace of cosine t. What is the middle piece? It is the Laplace of sine t. What is this? It is the product of the two Laplace transform, which is the Laplace transform of the convolution by the convolution theorem. So each of this is a Laplace transform. So Laplace transform of the linear operator. So it is the Laplace of C1 cos t plus C2 sin t plus Fh star sin t h. So y of t equal to C1 cos t plus C2 sin t plus 0 to t f of u sin of t minus u du is a complete solution. I asked you to derive this using the method of variation of parameters long ago, remember, last week. Which one? Which problem? Yeah, the same problem can be done in two ways. So you should do it by both ways and compare. Is the procedure clear? It's a very, it's nice and sweet. We get a solution presents itself as a convolution integral. This sine of t minus u that you see here is what is called as the Green's function. Okay. Right. That is one illustration about solving differential equations, initial value problems for ODEs. There are a couple of other things we can do using Laplace transforms. We are going to now demonstrate how to solve an integral equation, right, integral equations of convolution type. So, here is the first one, y of t equal to sinh t 1 minus sinh t integral 0 to t 1 plus u y of t minus u du. What is this object here? It is a convolution of two functions with the heaviside functions thrown in. Convolution of 1 plus t ht and y into ht, correct. So, take the Laplace transform of the equation, left hand side becomes capital Y, Laplace transform of 1 is 1 over s, Laplace transform of sinh t is 1 over s squared minus 1, please verify this, plus Laplace transform of the convolution is the product of the Laplace transforms. You see that over here, you see that over here. So, y equal to 1 over s minus 1 over s squared minus 1 plus 1 over s plus 1 over s squared, Laplace of t is 1 over s squared times capital Y, Laplace of little y is capital Y. So, once again you have capital Y into 1 minus 1 over s minus 1 over s squared equal to 1 over s minus 1 over s squared minus 1. Write just this expression please, because there is an exercise for you. Write down this expression and then recover y, correct. So, solve, get the solution y. So, we have used the method of Laplace transforms to solve a integral equation of convolution type. So, the integral appears in the convolution type integral. So, you can use Laplace transforms to do that. Because there are other methods of doing it, you can differentiate the integral and so on, you can convert it into an ODE, that is possible. I mean, I am not claiming that this is the only way. After you get the ODE, you have to solve the ODE, for which you will apply the Laplace transforms. That is, yeah. The next one is an exercise, solve the integral differential equation dy by dt equal to 1 minus integral 0 to t y of t minus u du. What kind of a convolution is this? Convolution with what? Convolution of yh with what? 1 or 1 into ht. 1 into ht, and there is an initial condition given because there is a differential first order derivative here present, correct. So, please do this straightforward, simply take the Laplace transform. The next slide you are going to see a very important integral equation called the Abel's integral equation. This is called the Abel's integral equation. Now, solve for yt given phi of t equal to integral 0 to t y of u du divided by t minus u to the power alpha. Assume phi of 0 equal to 0 and assume that phi is differentiable. You do not have to write all these comments because you are going to have the slides on Moodle. The fact that phi of 0, this equation will suggest to you that phi of 0 should be 0, right, when you put t equal to 0, but that is not required, that is not necessary, but you can assume it anyway. Nor is it required that phi should be differentiable, but you assume, let us work with the nice case. See, even if two functions are continuous, the convolution need not be continuous at the origin, because if you take ht by root t and ht by root t, take the convolution, it is pi times ht, and that is again discontinuous. That is the problem. So phi of 0 is not required. All right. This is called the Abel's integral equation. Abel's integral equation. Now, we will come to a nice physical problem. So, what is the tautochrone problem? What is the tautochrone? The word tautochrone comes from two Greek words. Tautos means the same and chronos means time, correct. So, the tautochrone problem is the following. You take a wire you take a wire, and how should I shape the wire so that a bead that slides down the wire takes the same amount of the time taken by the bead to slide to the bottommost point is independent of the height from where the bead is released. So, you take a wire, you take a huge wire, right, and you slide the bead from this end. It takes time t to reach the bottommost point. You release it from halfway down in the wire, it will take the same time. If you release it from 2/3 the way, it will still take the same time. That is the tautochrone problem. How should I shape the wire? Remarkable, isn't it? Do you think that it's possible? Such a thing is possible? What will be the curve? No, circle will not work. Catenoid will not work. Any other guesses? Cycloid, absolutely. Cycloid is the tautochrone. The least time is a different problem. That's called the brachistochrone property. The cycloid has two properties. Of all possible curves, which curve will take the least possible time to reach? That's the brachistochrone problem. Here I am talking about the tautochrone problem. That it's not that the curve is fixed. The time of descent is independent of the height from which it is released. So, cycloid satisfies both. It is both the brachistochrone as well as the tautochrone. So, it is this property of cycloid that you want to establish. All right, let us do that. So, that is the problem I had just explained to you, and this is a problem, that is you take a wire, the wire is drawn here, and it comes, the total height is y, or rather a general height for various starting positions. Take a general starting position, it is y, and the bead slides down, and the time taken for the bead to slide down in general will depend upon y, but we want to shape the wire in such a way that the time of descent is independent of the height of release. Whether you release it from here, it should take the same time. Whether you release it from here, whether you release it from here, it should not make any difference. It should take the same time to come down. Correct? Okay. So, let us take y to be the height from which the bead is released, and the bead is sliding down, and at time t let the height be eta. Okay. So, the vertical displacement is y minus eta, correct, and let us assume that sigma is the arc length measured from the origin. Sigma is the arc length along the wire measured from the origin, correct. So, what is d sigma by dt? D sigma by dt is the speed, correct. So, the kinetic energy is what? 1/2 m into d sigma by dt squared, correct. What is the potential energy? It is mg into eta, and this total should be constant, correct, all right. So, the total energy should be conservation of energy. So, what is the total energy? At the start, what was the speed? 0, correct. So, it starts from rest. So, the total energy will be the potential energy at the start, mgy, correct. So, the total energy is the potential energy at the start, which is mgy. So, the kinetic energy at time t plus the potential energy at time t is the total energy, or d sigma by dt the whole squared is 2g times y minus eta. So, take the square root, you get a negative sign. Why? Because as time evolves, the arc length decreases, right, as time increases, because the bead is coming closer and closer to the origin, then a negative sign. So, you integrate this equation, you multiply by dt and divide by this, root 2g times capital T. Capital T is the time taken to reach the origin, will be integral 0 to y d sigma by root of y minus eta. The minus sign will go away because at time capital T you are at the origin, and at time t little t equal to 0 you are here. So, although there is a negative sign, I switched the limits of integration. So, the negative sign goes away and we get root 2 gt equal to integral 0 to y d sigma by y minus eta. D sigma is a function of eta, so d sigma by d eta d eta. So, now what kind of a equation is star? What kind of an equation is star? It is a integral equation of convolution type. Right hand side is a convolution of sigma prime n 1 over root y. Right hand side is a convolution of sigma prime n 1 over root y. Take the Laplace transform, you get root 2g capital T by s equal to the product of the convolutions, product of the Laplace transforms. Laplace of 1 over root eta, Laplace of sigma prime. 1 over root eta is root pi by s, correct. So, this root s will cancel, one root s will cancel, the root pi will come below, etc. And so, the algebra, when you do the algebra, you get Laplace of sigma prime equal to t root 2g by pi into 1 over root y. 1 over root s, what is the inverse Laplace transform of that? What is the Laplace transform of 1 over root t? 1 over root t Laplace root pi by root s. So, after you do the algebra, there was a 1 over root s. So, you have to calculate the inverse Laplace transform of 1 over root s, that is how you get the 1 over root y. So, you get sigma prime squared equal to a by y, where a is a square of this constant. T root 2g by pi is a constant. T is a constant because the t is a time of descent, that is supposed to be constant. G is the acceleration due to gravity, that is constant. Pi is a universal constant. So, sigma prime squared equal to a by y. But what is sigma prime squared? Dx by dy squared plus 1, arc length. So, that is what it is. So, you get dx by dy is square root of a minus y by y. You get a first order separable ODE, variable separable ODE. It is convenient to put it in parametric form, y equal to a sin squared theta by 2. Put y equal to a sin squared theta by 2, this right hand side simply becomes cot theta by 2 dy. But dy is a 2a sin theta by 2 cos theta by 2 into half. So, if you put all those things together, the dx simply becomes a cos squared theta by 2 and dy is a sin theta by 2 cos theta by 2 d theta. So, both x and y can be calculated. X is a by 2 theta plus sin theta, y is a by 2 1 minus cos theta. And now, when the thing reaches the origin, y is 0. So, cos theta is 1. So, sin theta is 0 and theta is 0. So, psi must be 0. The boundary condition, terminal condition gives you that psi is 0. So, you simply get the, when you put psi equal to 0, what do you get? You get the equation x equal to a by 2 theta plus sin theta, y equal to a by 2 into 1 minus cos theta, this equation. So, the tautochrone is a cycloid, correct. Now, of course, what is the use? Interesting, but pretty useless, eh? But no, not quite. Huygens, Christian Huygens used this property to construct what is called as the isochronous pendulum. When you take the simple pendulum, the period depends upon the amplitude, it is not independent of the amplitude. only for small oscillations is it independent of the amplitude. So, if we allow the period to, if we allow the amplitude to be huge, it will not be independent. Okay. You want a pendulum wherein you want the period to be independent of the amplitude, correct. Simple pendulum will not do it. So, Huygens constructed the isochronous pendulum. Huygens did a lot of work on clocks. He wrote a book on clocks, Horologia Oscillatorum. It's one of the most authoritative account at that time. And here is a picture of his isochronous pendulum. So, you take two successive arches of a cycloid made out of a metal sheets, okay, and at the apex you suspend your pendulum. From the apex you suspend your pendulum, you just draw it aside and let it oscillate. So, while it is oscillating, what is happening? The string of the pendulum, is in contact. It winds along the arch of the cycloid. Part of it is free. When it is completely on the left hand side, it is completely with the cycloid, and then you release it, correct. As you release, the string partly is wound along the cycloid and part of it is free, and as it unwinds, greater part of the string is free. So, what exactly is this curve that the free end of the pendulum trace out? That curve is called the evolute. Given any curve, what is the evolute of the curve? You do exactly what I said. You take a string and you allow it to unwind. So, if you take a circle, for example, and if you wind a string around a circle and you release it, what will be the evolute? The evolute will be a spiral, no? Whereas here the evolute of the cycloid is another cycloid. The evolute of a cycloid is another cycloid, correct. So, the bob of the pendulum it traces out a cycloid. So, it will not depend, the time to reach the bottommost point will not depend upon the amplitude because of the tautochrone property of the cycloid, correct. Because the tautochrone property of the cycloid, the time it takes to reach the bottom will not depend upon the amplitude. So, you got a isochronous pendulum, a pendulum that has the same period, because as it oscillates the amplitude will go down eventually, correct, but then the period should not change. Remarkable invention, I must say. Huygens did a lot of work on pendulums. In fact, he constructed clocks, a variety of clocks he constructed, remarkable clocks he produced, Christian Huygens. Okay. So, this completes the chapter on Laplace transform, end of chapter 5, alright. G.F. Simmons, differential equations with applications and historical notes. There you will find the proof that the cycloid is the brachistochrone. G.F. Simmons, S-I-M-M-O-N-S, differential equations with applications and historical notes. You will find a proof that the cycloid is the brachistochrone. Okay. What we have established is a tautochrone property of a cycloid. Please, they are two different things. So, when you teach these things, make sure to keep them straight, okay, do not mix them up.